Assalamu alaikum. Welcome back to BIOS course. Today we have the lecture of analysis of categorical data. From the previous lecture that we have in general two types of data in statistics, quantitative and qualitative data. Our concern today is on analysis of categorical data. Okay, learning objectives of this lecture are how to conduct a formal hypothesis test of a claim about two population proportions. 2. Use categorical data summarized as frequencies in a table with at least 2 rows and 2 columns to conduct a formal test of independence between the row variable and column variable. And if possible, later we uh, will know how to conduct the cross tabulation and chi-square test using JUMP software. Okay, uh, so the focusing in this lecture will be on 3 points. Point 1 is inferences about two population proportions. Number 2, contingency tables, the concept and the idea of analyzing contingency table. And the third point is to do or to conduct inferences statistical test about the association between two variables. Again, 3 points. Point 1 is inferences about two proportion, concept of contingency table, and the statistical test used for inferences about association between two categorical variables. Okay, let us start with the first point, which is inferences about two proportions. In the previous lecture, we have seen that how to conduct statistical analysis or hypothesis testing for one population proportion. Okay, now the objective is to use sample data from two population to make inferences about this population. That means comparing two population proportions. Again, today or this point or in this lecture, we are going to see or to make statistical test to examine significant difference between two population proportions. That means we have two different population, and the objective is to examine significant difference between the population proportions. For examples, to see if smoking causes lung cancer. Okay, to see if smoking causes lung cancer. So we have two populations, two different populations in this example. Population 1 contain smokers, okay, smokers. Population 2 non-smokers, okay. The objective is to examine if there is significant difference, okay, in the proportion of lung cancer between the two different population, smokers and non-smokers. So we want to determine whether the smokers have a higher proportion of lung cancer compared to the proportion of lung cancer among non-smokers. This is what meant by two population. Population 1 is smokers, population 2 non-smokers. Sorry. Okay, requirements for inferences about two populations, and as I said before, okay, requirements, assumptions, and so on are very important to know. We have two requirements for conducting inferences about two population proportion. Number 1, the proportions are from independent simple random samples. Okay, sample values of two population are not related. We have totally separated population, and from each we pick a simple random sample. This is the first requirement. The second one is that for each of the two samples, the number of successes is at least 5 and the number of failure is at least 5. And we have seen before the concept of successes. Okay. Okay, here we have notations on inferences on two populations. For population number 1, okay, for population number 1, B1 is a parameter, which is population proportion. Small n1 is the size of the sample taken from population 1. x1 is the number of successes in the sample taken from population 1. And b had 1, which is a statistic, b had 1 is x1 divided by n1, okay, where b had 1 is the sample proportion. Q had 1, here we should have 1, Q had 1 is 1 minus B had 1, and Q had is a complement of B had, so Q had 1 is a complement of the proportion from the sample or from the first sample. The same notations can be applied for population 2. That means we have B2, N2, X2, B had 2, and Q had 2, okay, for the second population. Okay. Before starting conducting the test of two population proportions, also we need to know the concept of Boole estimate of B1 and B2. B1 is the first population proportion and B2 is the second population proportion. Okay, we need to do or to make some combining between B1 and B2. We need a measure combining B1 and B2. This measure is called Boole estimate. Boole estimate. So the Boole estimate of B1 and B2, which is denoted by B bar is B bar equal x1 plus x2 divided by n1 plus n2. Again, B bar is a Boole estimate, which is a measure combining first population proportion and the second population proportion, which is equal x1, and x1 is the number of successes in the first sample, x2 is the number of successes in the second sample, n1 and n2 represent sample sizes. Okay, Q bar, Q bar is the same. It is 1 minus P bar. It is a complement of the Boole estimate. Okay, here the test of hypothesis is concerned with testing whether there is significant difference between B1 and B2. Again, focusing on examining the significant difference between B1 and B2. And B1 is a parameter representing the first population proportion, and B2 is a parameter representing the second population proportion, and the objective is to examine if there is significant difference between B1 and B2. To do that, we start with stating the null and alternative hypothesis. And from previous lecture, in null hypothesis we have equality sign only. In null hypothesis you have equality sign. So the null hypothesis in inferences of two population proportion is stated as H naught B1 equal B2. This is constant. Okay, this is the null hypothesis. B1 equal B2. That means there is no significant difference between the first and the second population proportions. Alternative hypothesis can have three forms. Okay, either the first one is B1 doesn't equal B2, or B1 less than B2, or B1 greater than B2. The form of the alternative hypothesis is determined by the researcher's claim. So the researcher's claim or the researcher statement determine the form of the alternative hypothesis, which is also determines the type the type of the test. Okay, you have two tail test or one tail test. Okay, this is the equation of computing test statistics in inferences of two population proportion. This formula will be attached in exam. So Z equal B hat 1 minus B hat 2 minus B1 minus B2 divided by square root of B bar Q bar over N1 plus B bar Q bar over N2. Z is test statistic. Z is test statistic. Okay, Z represent test statistic. Okay, B had 1, this is the proportion from the first sample. B had 2, the proportion from the second sample. Also, uh, B1, okay, the proportion of the first population, and B2 the proportion of the second population, divided by square root of B bar, which is a pooled estimate, okay, of B1, B2. Q bar is a complement of B bar. N1 the first sample size, and N2 is the second sample size. Okay. In practical computation of Z, we ignore this part of B1 equal B2. Okay, because if we look in the null hypothesis, B1 equal B2, it implies that B1 minus B2 equals 0. So this part is equal 0, so ignore it in calculation. Note, in the examples and exam question, ignore the expression after the minus sign in the numerator. Okay, so ignore about this part. Okay. Let us have an example of computing or of making inferences on two population proportion. The example is about testing the effectiveness of vaccine. A USA Today article reported experimental results from nasal spray vaccine for children. Among 1,070 children given the vaccine, 14 developed flu. Among 532 children given placebo, 95 developed flu. The sample data are summarized below. Use alpha equals 0.05 as a significance level to test the claim that the proportion of flu among vaccinated children is less than the proportion of flu cases among children given placebo. Okay. To run the test, let us first summarize the findings given in the example. Okay. The example is about comparing the proportion of developing flu between two different populations. Population 1 represent children given vaccine, and population 2 children given placebo. So we have two different populations. Now let us summarize the finding. For the first population, vaccinated children, N1, which is the sample size taken from the first population, is 1,070. X1, X1 is the number of successes. Okay, so successes here represent number of children developed flu. It is 14. B had 1, so B had 1 is X1 divided by N1, so it is 0.01308. Okay, for the second population, children given placebo, N2, which is the sample size 532, X2, number of successes, the number of children developed flu is 95. So B had 2 is 0.178, which is X2 divided by N2. Now look here, before going on, be careful. What is the claim of the researchers? The claim is that proportion of flu among vaccinated children is less than. This is very important. So the researchers claim determines the alternative hypothesis. H naught is constant. Which is B1 equal B2. This is constant. No difference between two population proportion. H1, which is alternative hypothesis, depends on the researchers' claim. The researchers claim that vaccinated children, which is the first population, that means this is B1, is less than the proportion of flu in the second population. So H1, okay, as stated or claimed, B1 less than B2, and this is very important because the sign or the way or the form of H1 determine the type of the test, which is determine critical value, which is also determines the critical region and the criteria for making decision on the null hypothesis. Okay, so solution. Let's first check the requirements of the test. Remember, we have two requirements. Requirement simple random samples drawn from independent population, and we have two independent population. The first one, vaccinated children, and totally different from the second one of children given placebo. Also, the second requirement is that for each two samples, we should have at least 5 successes and 5 failures. 14 successes in one and 95 successes in N2 with a lot of failures in both samples. Okay, step 2 is state the null and alternative hypothesis. As we have seen, H0 is constant, B1 equal B2. This is constant. H1 determined on the original claim, and we see that B1 is less than B2. Alpha, which is the significance level, is 0.05. Very important to identify the critical value and critical region and so on. Step 4, calculate test statistics and start with the pooled, with the pooled proportion, which is x1 plus x2 divided by n1 plus n2. The answer is 0.068. Hence, Q bar complement is 1 minus P bar, it is 0.93196. Next, compute or use the formula and to find the test statistics, which is B had 1 minus B had 2. This is B had 1, B had 1, which is x1 over n1 minus, this is B had 2, which is x2 minus n2 minus, this is 0. Ignore about B1 minus B2 divided by B bar Q bar over n1 plus B bar Q bar over n2. The final answer is minus 12.39. Please check the calculation and try to do it by yourself. The final answer is minus 12.39. As we see in previous lecture, we have two ways or two approaches, on making decision. Number one is critical region and critical value, and number two is B value. Both approaches give the same conclusion. Let us see the B value. The alternative hypothesis, B1 is less than B2, therefore there is left-sided test. So the B value, when we have left-sided test, the B value, is the area to the left of the test statistics. And test statistics is calculated to be minus 12, which is very, very extreme value. And we know also from the table, any value less than minus 3.49, the area to the left is considered to be 0.0001, which is a B value. So the B value is a very small number, which is less than alpha, which is 0.05. So we reject the null hypothesis. Our decision is to reject the null hypothesis, and it implies that we have sufficient evidence to support the researcher's claim. Again, because the B value is less 0.001, which is less than 0.05, we reject the null hypothesis. So we support the alternative hypothesis and conclude that there is sufficient evidence to support the claim of lower flu rate for the first population, which is vaccinated children. The second point in the lecture is about the concept of contingency tables. Contingency tables are very important concept in statistics, because we have a lot of categorical data in statistical analysis, especially for survey analysis, questionnaire, and so on. Contingency table, focusing on the analysis of categorical, which is qualitative or attribute data that can be separated into different categories, called cells. The contingency table uses a two-way frequency table. We should at least have 2 rows and 2 columns, to have contingency table. We use chi-square test, a very well-known statistical test for analyzing contingency table. So chi-square distribution, which is the distribution used to analyze categorical variables or categorical data is one of the most widely used distribution in statistical application. Why? Why widely used? Because in general, when making or doing statistical analysis, a substantial proportion of data are categorical. So we use this chi-square test for analyzing the categorical data. Appropriate for categorical variables, marital status, for example, gender of students, educational level, and so on. All categorical variables are used or are analyzed using this chi-square test. Okay, this is a general idea of contingency table. For example, let us have this example of cross tabulation or contingency table of two variables. Here, this is exposure. Okay, this is variable one, which represents rows is exposure. We have two categories, exposed and non-exposed. Here we have disease status. Also, we have two categories, deceased and no disease. So a, for example, A is the count or frequency of individuals exposed, and at the same time deceased. B is the frequency of exposed and no disease. C, not exposed and deceased. And D, not exposed, not deceased. E and F represent total of rows. H represents total of columns, and N is the grand total, which is E plus F or G plus H. Okay, it is E plus F or G plus H. Okay. Hypothesis of chi-square test, null and alternative hypothesis. This is important. Okay, H naught, variable 1 and variable 2 are independent. You know, variable 1 is the one represents column or rows, doesn't matter, and variable 2 is the second one. Okay, are independent. This is very important. Okay, H naught, we assume, we claim, we state that there is no relation. Okay, both variables are independent. In the alternative hypothesis, variable 1 and variable 2 are dependent. There is relationship. Okay, sometimes said that not associated, okay, not related, the same meaning of independent, associated, or related, and so on. Okay, validity of chi-square test. This is important also. We use chi-square test when the observation are from independent subjects. Look here, this is important. Number 2, the expected, and we will see what expected values are not too small. Okay, for roughly no more than 20% of expected values should be less than 5, and none of expected values should be less than. Example, here we have contingency table between survival status and gender or age, anyhow. So this is for Titanic passengers. Does survival depends on being man, women, boy, or girl. Okay, survived and died represents rows, which is the first variable, which is survivalship. Gender, you can say gender and age, represents the columns. Okay, so we have 2 rows and 4 columns. This is the grand total. This is the total of all individuals. Okay, so H naught, the null hypothesis, the 2 variables are independent, or survivorship and gender are independent. Okay, before running the test, let us check the requirements. The sample is randomly selected, consists of counts of each data, okay, and observation are independent. H naught, whether a person survived, is independent of whether, okay, the person is a man, woman, boy, or a girl. H1, surviving and gender are dependent. Or simply we can say that H0 2 variables are independent and H1 2 variables are dependent. Okay, next, calculating test statistics. Okay, test statistics is chi-square. Chi-square is the test statistics, okay, equal summation O minus E square over E. O represents observed frequency and E is the expected frequency. O is the observed, okay, or given frequency, and E is the expected. So to calculate chi-square test, we need first to compute E, which is expected. E for each cell equal row total times column total divided by grand total, okay, which is the number of all frequencies in the table. For example, here we have the observed frequency, the given survived men, for example, are 332, died boys are 35, and so on and so on. This is the observed. So start calculating expected for each cell. And no, we have 8 cells because we have 2 rows and 4 columns. So number of cells is 2 times 4, number of rows times number of columns. So we have 8 cells. For each cell, the expected is column total or row total times column total divided by grand total. Again, this is cell 1. Okay, this is cell 1, which is men survived. So expected for cell 1 is row total, which is 706, times the column total, which is 1692, divided by the grand total, which is 2223. Okay, again, see the row total, multiply row total by column total and divide by the grand total. So the expected value for cell 1 is 537.36, but actually the observed or the real number is 332. Let's say for boys died, for example, this is the observed 35. So the expected should be row total of the cell, which is 1517, times column total, which is 64, divided by the grand total, which is 2223, and so on. Now, this is the observed, 332. This is the observed, okay, and here is the expected. This is the expected. Expected means expected value or expected count in assumption of independence between two variables. And these are the expected for all cells. These are the expected for all cells. Chi-square, chi-square is summation. It is summation O minus E. It is O minus E. This is O minus E square divided by E. Okay. For each one, O minus E square divided by E. So this is for cell 1, O minus E square divided by E1 or by E, and so on for the last cell. Sum up all the findings. The final answer is the chi-square value or chi-square statistics, which is 507.084. Very big number. Okay, step 4, significance of level is 0.05. Okay, this is given. Okay, 0.05. So how to make decision on the null hypothesis in chi-square test? Number 1, we need to know the value, the critical value from the table. We need to know the critical value from the table. This critical value in chi-square test depends on the parameter called degrees of freedom. We need first to identify or to calculate the degrees of freedom. Degrees of freedom in chi-square test is R minus 1 times C minus 1. R is the number of rows and C is the number of columns in contingency table. In our example, we have two rows and we have 4 columns because we have 2 categories in the first variable of survival, and we have 4 categories in the second variable of each gender. So it is 2 minus 1 times 4 minus 1, so the degrees of freedom is 3. As a concept of degrees of freedom is very important in chi-square test or in statistics in general. I think we can later discuss this concept in details, but here you need to know how to calculate the degrees of freedom in order to identify the critical value. So degrees of freedom is 3, alpha is 0.05. Then go to the given chi-square probability table. Here is the degrees of freedom, which is 3, and alpha, which is the significance, is 0.05. So intersection between 3 and 0.05, we find 7.815, which is critical value. This is a critical value. Okay, then chi-square distribution is not symmetric. It looks like this. The chi-square distribution is something like this. It is skewed to the right. Chi-square, it is skewed to the right. It is not symmetric. Okay, that means test of chi-square is always right tilt. In all cases, chi-square is right tilt. Okay, so let us now determine the critical region. The critical region, we need to know the critical region, which is the area to the right, lead to rejection of null hypothesis. The value here, which is a critical value, is found to be 7.815. So this is the critical region. This is the area of rejection of the null hypothesis, and this is non-critical region. What about our test statistic? Our test statistics value is a very big number, which is 507 point something. So this value is fall within critical region. Okay, our test statistics fall within critical region when, and you know, when test statistics fall in critical region, we reject. Okay, the decision is to reject the null hypothesis. Again, chi-square distribution is always right tail because it is not symmetric, it is skewed to the right. First, identify the critical value from the table, and critical value depends on 2 parameters. The first one, which is the important one, is the degrees of freedom, and degrees of freedom is C minus 1 times R minus 1. You know, C is the number of columns and R is the number of rows. Then identify the significance level, which is always 0. Or in most cases is 0.05. So interaction or intersection between degrees of freedom and significance level give you the critical value, which used to separate the curve into critical and non-critical region. This is chi-square. As I said, this is chi-square distribution. It is something skewed to the, it is always skewed to the right. This is a critical value. Okay, it's critical value from the table of chi-square, which is 7.815. So this area of red, this red area is the critical region, and you know, from, yeah. Okay, using alpha 0.05 significance level to test the claim that when the Titanic sank, whether someone survived or died is independent of whether that person was man, woman, boy, or girl. The chi-square test fall in the critical region. Thus, we reject the null hypothesis. This is a decision to reject the null hypothesis at alpha equals 0.05 and concludes that when Titanic sank, whether someone survived depend. Okay, depend, because now we have sufficient evidence to support that there is a relationship or the 2 variables are dependent, whether the person was man, woman, or a boy. Okay, here are how to use jump in chi-square test. I don't know if we can have the possibility to do that later. Okay, problems, more exercises will be uploaded in Blackboard for your practice of chi-square test and inferences about two proportions. And see you later. Okay, Assalamu alaikum.